Welcome back. In the previous video, I covered the background concepts needed to understand what I will talk about in this video. Namely, how do we perform decision function attribution for gapped-Kamer SVMs using integrated gradients? Specifically, I will talk about SVMs with weighted gapped Kamer kernels and SVMs with weighted gapped Kamer RBF kernels. In this slide, I will focus on WGKM kernels. What we have done is essentially applied the integrated gradients formula explained in the previous video to a differentiable version of the WGKM decision function. The full derivation of the resulting formula is in the paper, and here we focus on the intuition and explanation of the results. So here is the WGKM decision function for sequence SX, calculated using the WGKM kernel similarity scores of sequence SX with each of the support vector sequences. And here is the part of the decision function attributed to position I of sequence SX. And what does it turn out to be equal to? Nothing but a summation of the weighted contribution to position I from each of the support vectors. The contribution to position I from support vector SZJ is given by CWGKMI SX, SZJ. In the next slide, I'll explain this term in more detail. So as you can see, the formula for CWGKMI SX, SZJ is rather intimidating. But it turns out to be simple once you work through an example. And that's exactly what we do here. So there are two summations in this formula. The outer summation, here, iterates through all the Elmers in sequence SX that contain the position I, the position of interest. The inner summation iterates through all the Elmers in sequence SZ, which is the support vector. So essentially, we're simply looking at all the Elmer pairs which can have a contribution to position I. And how are we figuring out the contribution to position I from an Elmer pair? We are simply seeing whether the Elmer pair is a match or not. And if so, we note what the overall contribution is. But we can't simply attribute the entire contribution to position I of the Elmer. We must distribute it equally amongst all matching positions, and only take position I's part as the effective attribution to CWGKM. And now we're really ready for that example. So in the example, we are focusing on finding out the attribution to position I equals 2 of sequence S1 from support vector SZ. We have assumed that initially we chose Elmers of size L equals 4, with K equals 2 non-gap positions. So exactly in line with the formula, we must iterate through the Elmers in S1 that contain position 2, and these are only the Elmers U0 to U2. And of course, in the support vector SZ, we must iterate through all Elmers, which would be Elmers U0 to U7. So we don't actually show all these 24 pairs of Elmers, but only take 3 representative examples to illustrate the types of cases encountered when attribution is being done. So here, in the first case, we are looking at Elmer U2 from S1 and U1 from SZ. The position of interest, which was I equals 2, is the first position in this Elmer. Now, this Elmer pair has the number of mismatches as 1. So according to the original formula shown earlier, it would have generated a contribution of H of 1, which is L minus M choose K, or 3. But the effective contribution to the position of interest is only 1/3 of that, since there are 3 matching positions in Elmer U2, corresponding to the G, C, and T. So the net attribution to the position of interest is 1, as shown here. Now consider the second case, where we look at Elmer U0 of S1 and Elmer U1 of SZ. Here the number of mismatches is 2. So it should have a contribution of h of 2, or 2 choose 2, which is 1. But this contribution cannot be attributed at all to the position of interest, since the position of interest has a G, and it is not one of the matching positions. So the net attribution to the position of interest is simply 0. In the third case, we look at Elmer U1 from S1 and Elmer U7 from SZ. Here the number of mismatches is 3, so it should have a contribution of h of 3, or 1 choose 2, which is 0. So even though there was a match at the position of interest, the net attribution to it is still 0, because this Elmer pair would not have had any common gapped k-mers at all. It would not have had any contribution to the kernel function. So hopefully by now, how the formula above works should be fairly clear. In this slide, I'll cover attribution for WGKM RBF kernel SVMs. At a high level, the formulas here are quite similar to those for the WGKM kernel. So the WGKM RBF decision function is calculated using the WGKM RBF kernel similarity scores of sequence SX with each of the support vector sequences. And similarly, WGKM RBF SVM IG SXI is the part of the decision function attributed to position I of sequence SX. And this is a summation of the weighted contribution to position I from each of the support vectors. The contribution to position I from support vector SZJ is given by CWGKM RBFI SX, SZJ. In the next slide, we'll explain this term in more detail. And here is the formula for CWGKM RBFI SX, SZ. Notice that all the quantities on the right-hand side are all previously explained quantities for the WGKM kernel. The quantity labeled term 1 is simply the WGKM RBF kernel output, or WGKM RBF similarity score for sequence SX with support vector SZ. Term 2 can also similarly be considered to be WGKM RBF kernel output, or WGKM RBF similarity score for a sequence SX dash, such that the dot product KWGKM SX dash, SZ is 0. Or in other words, it is the WGKM RBF kernel output for a baseline sequence, which has a 0 dot product with the support vector. So in that sense, term 1 minus term 2 becomes a difference from the baseline. And then CWGKM RBFI SX, SZ can be thought of as distributing this difference from baseline in proportion to CWGKM I SX, SZ divided by KWGKM SX, SZ, which is the fractional contribution to position I of the WGKM kernel output. And with that, the description of the decision function attribution of GKM SVM kernels is complete. Thank you for watching.